Howdy, math neighbors. Friendly neighborhood math teacher back with another math video, this time AP Calculus edition, specifically from the Calcmetic Differentiability Practice Assignment, problems number 4 and 5, the piecewise functions. We're going to treat these the same way as we did with the continuity questions. Namely, we're going to think about the piecewise function in pieces. And then we're going to look at the place where the two pieces of the piecewise function meet. If we had more than two pieces of the piecewise function, then we would have to do multiple pieces and multiple x values for possible connection. So I've written here analysis for the first piece. That's when x is less than 2. So I wrote it as the interval from negative infinity to 2. I'm going to write now the interval from 2 to infinity. This is the other piece. In both cases, the justification is the function presented is a polynomial function. And we know that polynomial functions are continuous. And I also want you to know that they are differentiable. You can use polynomial to support claims of differentiability just like you can for continuity. So this means we are left considering the continuity at x equals 2. When we consider continuity, we look at the limit existing. So first, the limit as x approaches 2 from the left using the top piece and substitution, got 5. And then the limit approaching 2 from the right using the bottom piece, 4x minus 2. This time I got 6. Since the limit from the left does not equal the limit from the right, that means this function is not continuous at x equals 2. Because the function is not continuous at x equals 2, the function is not differentiable at x equals 2. So you could describe f of x as non-differentiable, but once again, I think it is beneficial to be specific and say not differentiable at specific values of x rather than describing the function as non-differentiable. That's again because we can apply the properties of differentiability to the parts that don't have the limitations that this function has at x equals 2. So we're going to turn our attention to number 5, and in number 5, we're going to do something very similar. You'll notice that my justification here is slightly different for the differentiability of the two pieces. This time I mixed it up by declaring specifically what kind of function we have. So they are polynomials, but the first one is linear and the second one is a quadratic, which is equivalent to saying they are polynomial functions. And polynomial functions have all of the necessary properties to generate differentiability for all input values across their domain. And that means we're going to have to do a differentiability analysis at the place, the x value, where the two pieces are joined, which is x equals 1. My purpose here was just to mix it up a little bit to show you that you have some flexibility when writing your justifications. So we know when it comes to differentiability that there are two things that must be true to conclude that the function is differentiable. In this case, we're specifically checking x equals 1. So we want the limit approaching x equals 1 from the left using the top piece, that is 0. Got that with substitution. And the bottom piece, approaching 1 from the right, also is 0. This means the limit as x approaches 1 for the function f of x exists, has the value 0. And the second part, f of 1 is 0, which means the third part of continuity, the formal definition of continuity that is satisfied because the value of the function and the value of the limit are the same. So all of that work to do one part of the definition of differentiability. We've shown that the function f of x is differentiable everywhere except 1. We've shown that the function is continuous at x equals 1. We must satisfy the second part. Now, to satisfy the second part, the slopes must be the same. And remember, I've written here, if you haven't noticed, the notation f prime of x. So f prime of x is also a piecewise function. It has one piece when x is less than 1 and another piece when x is greater than or equal to 1. The first piece has slope of 1. The second piece has slope of negative 2x. And again, the derivative, f prime of x, for this specific function is the slope of the line tangent to the function. And for right now, the only way we have of showing how we might get a formula for the slope of the line tangent to the function is by using the formal limit definition of the derivative. So I do f of x plus h, which is, as I've written, negative 1 plus the quantity x plus h minus f of x, negative 1 plus x. Distributing negative signs, combining like terms. That gives us h over h. H over h is 1. The limit as h approaches 1 of 1 is 1. Repeating the process with the other piece, negative 1 plus x squared. We have, positive 1 minus x squared. We have 1 minus the quantity of x plus h squared minus the quantity 1 minus x squared. Again, the second quantity, 1 minus x squared, is f of x. If we apply the distributive property to x plus h quantity squared, we get four terms: x squared, two xh's, which I've written expanded here, but you could certainly write immediately as 2xh plus h squared. Similar to the last one, we are looking for like terms to combine. After combining like terms, we are hoping to finally have the ability to change the value of this limit from something that has 0 in the numerator and 0 in the denominator, an indeterminate form, into something that does not. And we do, because we can factor h out of both terms of the numerator. That is a common factor with h in the denominator. So we have negative 2x plus h, which, as h approaches 0, is negative 2x. So all of that work just to finally arrive at the place where we can consider the slope approaching 1 from the left. So the limit as x approaches 1 from the left for f prime of x. We use the first piece, which is 1. Then we consider the limit as x approaches 1 from the right. We are going to use the piece for f prime of x, negative 2x. That value is negative 2. Since those slopes are not the same, we have a function that is differentiable at all values of x except 1, continuous at all values of x, including 1, but it makes false the second part of the definition of differentiability. Consequently, this function is differentiable at all values except x equals 1. Hope you have enjoyed this video and narration. I've tried to write out exemplar work that you can use to pattern your responses after in the future. And if you enjoyed the video, you know how that works. Do it. Thanks.